Okay, and now we are headed to the last lecture by Matt Stoffregen.
Great. Yeah, thanks. Yeah, now we're headed to the third half of the talk, to quote Car Talk. I don't know if anyone, Car Talk has been off the air for a while. But it's still the third half. So the goal in this part will be that we want to actually prove this theorem, and then at the end, hopefully we'll finally say something about monopole Floer spectrum. So yeah, just to rewrite our notation from last time, associated to a spin-closed Floer manifold. Now maybe let's make an extra assumption to make some of what we'll do more convenient, a little bit more convenient. So we'll assume that it has vanishing first homology. And we already know that associated to this, we've gotten something called the Bauer-Fruita map, which is a map from a sphere that has dimension negative the signature times the quaternions, and it's going to some other representation sphere. So, and this is a pin 2 equivariant map. And in this part of the talk, let's just say G is always pin 2. So G will be pin 2 from now on. Right. But at first, this doesn't seem so great because, what can we actually say about X knowing that we have an invariant here? First of all, it's kind of annoying that this group may be something that we don't understand at all. Like, you should view the homotopy classes of maps between two spheres as something that's basically incomprehensible. This is, even worse than the stable homotopy groups of spheres. And the other problem is that this might just always be 0. Like, what if we defined an invariant and it was just 0 for everything? So first, let's give a short justification for why this invariant is not totally boring. So because the Bauer-Fruita map is a map between two G spaces, it takes the fixed points of one G space to the fixed points of another. So we can consider the fixed point map associated to it. So we can take the G fixed points. So the upper symbol just indicates that we're going to restrict the map to the G fixed points. And then it becomes a map from a 0 sphere because the fixed points of this sphere are a 0 sphere, and the only points fixed by all of pin 2 in this sphere are also the 0 sphere. So somehow the fixed point map is actually a map from S0 to S0. Now, there aren't very many maps from S0 to S0. You might think there's just 2 maps. But technically, maybe we want to consider stable maps. So this is actually an element of the stable homotopy group of S0 to S0. But now there's no G subscript, right? The G fixed point map is just a non-equivariant map between those two spheres. But, in the limit, if you stabilize a bunch of times, this is just Z. There aren't very many maps from S0 to S0, but there's at least a Z from Sn to Sn for other n. But you can actually use the definition. So just from the definition of the Seiberg-Witten map, it's actually easy to calculate this because there aren't very many fixed points in the domain and codomain of our very Fredholm map. So you can calculate this map explicitly, and it's the identity, or plus or minus the identity. But for now, let's choose conventions so that it's just the identity map. But this is really good, actually, because the fact that the fixed point map is not null homotopic tells you that if you have a closed spin Floer manifold, the Bauer-Fruita map cannot be 0 because its fixed points have to be a non-zero map. So actually, for any closed spin Floer manifold, it automatically has a non-trivial Bauer-Fruita map. That may not be very useful, but at least it's not exactly the 0 map. All right, and now using this, we can just see, well, what can we say about sigma and B2 plus from knowing that there's such a map? So what do we know about sigma? What can we say about the signature in B2 plus? And actually, just for convenience, let's choose some additional notation. Let's say that the intersection form, so right, the second cohomology of X is going to be equipped with some intersection form. And if it's a spin manifold, you can say that this is always going to be some number of pieces of E8. And we'll choose negative E8 for reasons of convenience. So it doesn't really matter what this is. It's the E8 intersection form, but it's negative definite. And it's even. Those are the only things we need. And then plus q times the hyperbolic intersection form. So this one is easy to write down at least. But all we need to know about the hyperbolic one is just that it's a bilinear form of signature 0. And it's two-dimensional. So the intersection form of any spin manifold is going to be some number of pieces of E8 and some number of pieces of H. And we can rewrite this. You can sit down and sort of rewrite the signature in terms of P and B. You can rewrite these two things in terms of P and Q. And I won't actually do that, but just as an exercise. These are PQ, B2 plus, and B2 minus. In particular, if we have a map like this, so let's say we have BF XS, that's a map from S to the negative sigma X H over 16. And this is actually just 2P, or this is P over 2H. So that's just, once you rewrite it in terms of P and Q. And it's going to SQ R tilde. So B2 plus is just Q. So you have a map like this. But you also have how the fixed points fit in. And you know you have a commutative diagram like this, where on the bottom you just have the identity map. Right? That's our claim that on fixed points the map is the identity. Great, cool, you have a commutative diagram. What are you going to do with it? Maybe I should say what we're actually going to try to do. So the Feruta's 10/8 theorem says that the B2 of X, so the second Betti number of our 4 manifold, is at least as large as the signature times 10/8. So, yeah, somehow this says that, oh wow, that's totally unreadable. Can anyone see that actually? Okay. Let's see. Sort of readable. So this says that the rank of the second cohomology, it's got to be at least some amount bigger than the signature. So to illustrate why this theorem is interesting, this is for X as above. The reason this theorem is interesting is that there are plenty of topological manifolds that violate this. So counterexample. Friedman showed that any intersection form can be realized by some topological form manifold. So you could choose, there exist topological form manifolds whose intersection form, so in keeping with Sergei's lectures, I think his intersection form was B. I think maybe we want it to be Q, actually. So the intersection form is Q, but you could choose it to just be E8. That's totally okay. And you can choose that to be a topological spin form manifold. But that's negative definite, which means that B2 is actually equal to the absolute value of the signature. So indeed, there's lots of topological form manifolds which will fail this inequality. So that's kind of neat. And this theorem says that although those topological manifolds exist, none of them can be smoothed. And you could ask, like, what are the ratios of these two numbers that we know actually exist? And there's something called the K3 surface, which has its second Betti number is equal to 11/8 the signature. So, and that's actually the minimal ratio known. So you can take connected sums of K3 to get many manifolds that have their second Betti number equal to 11/8 the signature. But right now it's unknown if there are any manifolds that fit in between these two slopes. So it's not known if there's a spin manifold where B2 is less than, or where the ratio of B2 to the signature is less than 11/8. But at least Furuta says all the topological manifolds, below 10/8 are not in the way. None of them can be smoothed. But there's this small gap where we don't know what happens. And it turns out that that's exactly the last cases of the geography question. So the geography question asks, if you have a topological four manifold, or which topological four manifolds have smooth structures? And the answer to that is known for simply connected four manifolds, except in the slot of spin four manifolds where B2 over the signature is between these two values. So those are the only topological manifolds where it's not known if they have a smooth structure or not. So yeah, this question is basically the last case of geography for four manifolds. So that's pretty neat. And that also explains why this theorem has an unreduced fraction. So that's why it's the theorem on unreduced fractions, because you really want it to be the 11/8 theorem, but you're stuck here. So you can't reduce the fractions, because that would ruin the symmetry. All right, so that's what we want to show. And the exercise I should have written over here is you can check that that claim is equivalent to, we want to show that Q is greater than or equal to P plus 1. So that's what we'll do in the rest of this. So as long as you have a diagram like this, we're going to show that somehow that implies Q is greater than or equal to P plus 1. So yeah, that's the plan. But how would you do that? Well, if you want to analyze some diagram of spaces, you should apply a homology theory to it. But now we're going to have to apply an equivariant cohomology theory. So let's apply something called equivariant K theory. So we're going to take, at each slot, the equivariant K theory. Whatever that happens to be. Right, an equivariant K theory is like ordinary K theory. It's the set of bundles over your space, but now instead of bundles over, vector bundles over your space or complex vector bundles over your space, we're going to take G equivariant complex vector bundles. And really, these are all reduced K theory. So, you don't consider what happens at the base point. So we're going to list a bunch of properties of it. So the first property of equivariant K theory that we need is that Kg of S0 is the representation ring of G. So that just says that what are the vector bundles over a point? That vector bundles over a point are just the same thing as G representations. So K theory of a point is just the complex representations of G. And for our example, that's just going to be a ring on two variables, Z and W, that satisfy these two relations. So 2 times W is W squared, and Z times W is W squared. It doesn't matter too much what they are, but we'll need them later. And also, W and Z come from the representations that we've considered so far. So W is what's called the Euler class of C tilde. C tilde is the complex representation made up of two copies of the representation R tilde we talked about before. So we're only interested in complex representations. So R tilde is not good, but if we take two copies of it, it's a complex representation. And Z is something called the Euler class of the quaternionic representation. So in some sense, all the representations show up from the ones we've already seen. Great. A second observation is that Kg is a module over Rg. If you have any vector bundle over a G space, you can tensor it with a G representation, and that'll give you a new vector bundle. So this is actually a diagram of Rg modules. But each of these, so each of these has some Rg action, and the things on the bottom really just are the representation in Rg. Right, what's the only other thing that ever is useful about K theory? Pop quiz. or I mean, I'm being overly mean to K-theory, but what's the most important thing about ordinary K-theory? Well, there's basically only one thing I remember at least about ordinary K-theory. Yeah, I don't know. You have Bott periodicity. Right, you have Bott periodicity for K-theory, which says if you suspend, S0 by S2, if you take a space and you smash it with S2, you don't change the K-theory. But you're not supposed to think of Bott periodicity in that case as being something too periodic. What would be natural to think of it as saying that ordinary K-theory is invariant under suspending by complex representations of the trivial group. And actually, Bott periodicity also works fine for K-theory, for general equivariant K-theory. It says that Kg, if you suspend a space by a complex representation, it's isomorphic to Kgx. But actually, all these different spaces are suspensions of S0 by a complex representation. Unfortunately, this thing is not necessarily complex, so we're just going to assume Q is even so that life is easier. So if we assume that Q is even, then all these entries are suspensions of the zero sphere, so they're actually all copies of RG. So now we have 4 RGs and we have some RG linear maps between them. But Bott periodicity is even better in the equivariant setting than in the non-equivariant setting because you have a map from S0 to SV in the equivariant setting. You can just include the North Pole and the origin inside of your representation. In ordinary K-theory, this map is trivial. But in equivariant K-theory, it's a map from both the K-theories are RG, so it's a map RG to RG. But it's multiplication by the Euler class. So it's multiplication by the Euler class of your representation. And we just said that there were some Euler classes up there. So actually, these maps are just maps by Euler classes. And the Euler class of P2H is just, z to the p over 2. Very sad. You get z to the p over 2. Because you have p over 2 copies of h. And here, you don't get q copies, but you do get w. Oh, wait. You got w to the q over 2. So yeah, all 4 entries are just RG, and you have that. And this is just some f. You don't have any idea what it is. But now we have that diagram, and we can just say that f times zp over 2. Equals wq over 2. And then you look at the relations up there, and you ask what could be going on here. And in order for f times zp over 2 to be a multiple of w, you can just look at the relations and see that q over 2 has to be at least p over 2 plus 1. Right? Because, in order for f times times p over 2 to be a multiple of w, f had better be a multiple of w. And once it's a multiple of w, you get out at least p over 2 plus 1 copies. And then you just, you get p plus 2 is less than or equal to q. At this point, though, that's not quite right because we assumed q is even. You can fix our assumption that q is even, but there's a cost. You have to get rid of one of the ones. Right? So you wind up proving that p plus 1 is less than or equal to q. And that's what we needed. So somehow, we just showed, right, on these boards that this inequality holds. In fact, this is actually slightly stronger. Q is greater than or equal to P, proves the 10/8 inequality, but we actually showed that Q is greater than or equal to P plus 1, so it's slightly stronger. But yeah, that may seem like it's from outer space, because like, did we ever have to really think about these maps? No, not really. It was just algebraically guaranteed for us. As soon as you had a certain kind of map on fixed points, it became very hard to get a map between these two spaces. And that sort of makes sense, right? If the dimension of this sphere is really large, you can imagine it would be difficult to somehow squish the whole sphere down into this Q-dimensional one in a manner that's already restricted on the fixed points. And all we did was make that precise using some kind of fancy technology, but actually fancy technology that's been around for a while. We just showed that, right? Yeah, I mean, if this sphere is too big, there's no way to crush it into that lower sphere and keep the fixed points in the right spot. Which is, you know, reasonably, that's kind of plausible, but yeah, we just saw that there actually are algebraic tools to make it happen. But anyway, I think that's a really fun proof, because all you need is a couple of properties, and then it just does it, it handles itself, basically. Okay, but yeah. Between this and Donaldson's theorem, these are essentially the only constraints that you can get on what topological manifolds have smooth structures. All right, cool. Any questions on that part? Otherwise, we'll go on to monopole Floer Spectra.
Sorry, Matt.
Yeah, go for it.
Stupid question. Maybe
Yeah.
I couldn't really follow all details. So just overall, in the definition there, P and Q appear only in that, well, in red, so in the red diagram, right?
Yep.
And because, yeah, so that, for example, that variety is just 2 and Z. There are no P and Q there. On the first,
sorry,
on the
which
right-hand side. Yeah, so that one.
Yep. Yeah, so the P and the Q are just, I didn't actually say how the Euler classes behave with respect to multiplication. So yeah, that's...
But it's interesting, so it
So
looks
it-
like something that I would like to see in other contexts.
which part?
Not just the P and Q, how they play out. Like it has, well,
yeah.
something is similar to PQ torus, not.
Yeah.
I'm not.
Yeah, the only entry of the P and the Q is just, so you have this sphere, and the image of its, of the dual of the inclusion map. So including the fixed points into this high dimensional sphere, the map it induces on K theory is you apply the Euler class like P over 2 times. So this is, you've done P over 2 suspensions by H, and each one of those suspensions, when you map backwards, you get a Z. So you just have this Z to the P to the 2 term going this way. And, but if you follow the other way around the diagram, if you see where RG from the smaller representation goes, its Euler class is just going down to W to the Q over 2. And those are the only entries of the P and the Q in the theorem.
That's my point. It seems very, well, very light, and then you conclude something very strong.
Yeah, exactly. This proof is very, indeed, yeah. The amount of lightness of proof to the topological output here is basically a local maximum. So, yeah. But also, I mean, it seems like these are pretty heavy properties, but this is all,
of course,
these aren't even that difficult to prove, actually.
Thanks.
Yeah. Peruta did it. It's a very nice argument, yeah. All right. Great. So, okay, that was supposed to be some motivation to say that the Bauer-Peruta invariant is interesting, because, like, look how well it does on the geography problem. But I should clarify, maybe this is just an extended remark, sort of lost control of time, so maybe we could just do the fun remarks instead of the serious remarks. This Bauer-Peruta invariant is also defined for any spin C structure. So if S is a spin C structure, I guess those also came up on Wednesday, but if S is a spin C structure, the Bauer-Peruta invariant still makes sense. Somehow the chalk is, maybe I need to switch pieces. The Bauer-Peruta invariant still makes sense. But it lives in a slightly different group. Right, it's a map in this map between spheres. But now you don't have a pin-2 symmetry anymore if you don't have a spin structure, so you just have a circle symmetry. So these are two S1 equivariant representations. But you could ask, like, yeah, what can the Bauer-Fruit invariant be? And we should say that if the difference in dimensions of these spheres is 1, then we have a sort of Hurewicz map. So if the non-equivariant index is 1, then there's a Hurewicz map, which we'll just call H, from that homotopy group. So maybe we'll just call this, I don't know, M of S. So it's whatever the representation associated to the spin C structure was, to Q2 plus R. There's a map from this to Z. And it's actually an isomorphism. And even worse, it's also basically an isomorphism from the pin-2 equivariant version to Z. So this is, yeah, when the total index is 1. So if you forgot the equivariant structure, this would be maps from S1 to S0. Of course, ordinarily, there's not a Hurewicz map from the space of maps from S1 to S0 to Z. But in the equivariant setting, there is such a map. And this is an isomorphism. The image under that isomorphism of the Bauer-Fruit invariant is what people usually call the Seiberg-Witten invariant. So the Seiberg-Witten invariant is something integer valued instead of something valued in that crazy group. And there's various ways to construct four manifolds that have non-trivial Seiberg-Witten invariant. This can be done, you get some value in Z. We won't say anything about how you would do it. But as far as is known, the only four manifolds that have non-trivial Bauer-Fruit invariant, or at least the ones that have been constructed so far, where you take manifolds with non-trivial Seiberg-Witten invariant and their connected sums. So over here, let me just make a remark that the Bauer-Fruit invariant of a connected sum is the smash product of the Bauer-Fruit invariant of the pieces. So yeah, it makes sense to smash maps together, like it makes sense to smash spaces. And all examples, all four manifolds, all calculated examples with Bauer-Fruit non-zero are either connected sums of manifolds with, are actually, we can just say it all in one statement, are connected sums of manifolds with SW non-zero. So to put it another way, you would really like to know the answer to the following question. Are there irreducible, so not expressible as a direct sum, as a connected sum? Are there irreducible four manifolds X with Bauer-Fruit at X not equal to 0, but Seiberg-Witten at X equals 0? And you know, you would think that that should be true because, well, the Seiberg-Witten invariant just lives in Z. So that, you know, it doesn't have a particularly interesting home. But the Bauer-Fruit invariant is supposed to live in this very strange, potentially, you know, very complicated abelian group as you vary these coefficients home. And as far as we know, that it never does anything interesting if you have an irreducible four manifold. So, yeah, I guess I'm just, in keeping with what Sergey was doing, you know, that would be a hard question. That's not a homework question. But it's a curious one nonetheless. So I don't think there's really any good strategy to do that at the moment, but maybe we could say a little bit about how people well, how people would like to be able to calculate invariance of closed form manifolds. But yeah, any questions on the setup? All right, cool. So maybe what we would like to do is, let's say you have a closed form manifold, well known to just look like that. And you want to calculate Bauer-Fruta invariant of X by cutting it into pieces. So let's say it's X1, X2, X3. It would be great if you could somehow calculate the Bauer-Fruta invariance of the pieces and then recover the whole Bauer-Fruta invariant as the composite. And it turns out that you can do this. So, but you have to make sense of what it means to have a Bauer-Fruta invariant for a non-closed form manifold. So it turns out for Y a spin C free manifold, enclosed as always, you can construct something called SWF YS. Hopefully that's visible. Yeah, you can construct something like this, which is an S1 equivariant stable homotopy type. So that means it's well defined up to stabilizations. Like, it's not, as a space, it's not well defined, but once you suspend enough times, it's well defined. And if S was actually a spin structure, it would be a pin2 equivariant stable homotopy type. So these were originally constructed by Manolescu in the case of B1 equals 0, and the pin2 and S1 cases are the same difficulty. But in order to make sense of this more generally, you have to use the version for positive B1, and the version we'll need for that today is just due to conduit, Lin, and Sasahira. So we'll use the KLS version. So yeah, we've assigned some sort of invariant to each of the three manifolds in between. But then we'd also like to have an invariant for a four manifold that doesn't have boundary on one manifold, or that has boundary. Yeah, I should have said that the definition of that object is, it's very similar to the argument from the first talk today, where we did some kind of finite dimensional approximation procedure. It's a little bit different because the finite dimensional approximation here spits out a space instead of a map between spaces, but the moral idea is pretty much the same, although it's a lot harder there. And for X of four manifold with boundary, so say X1 has boundary Y1, and everyone in sight is spin C, you can repeat the finite dimensional approximation from the first part, this time mostly in the same way, and you get a map Bauer-Fruta of X1, which is defined from a sphere. And in fact, we can make the sphere precise. Which is to say you can calculate the index like we did in the first part. And you get a map to SWF of the boundary. So yeah, there's some invariant you can assign to the inner pieces, and that if you have cobordisms, you get a map between them. And if you have a cobordism with more than, with actually two ends instead of just one end, you get a map between the two pieces. So if X2 is a cobordism Y1 to Y2, you get a map like this. So that all that's suspended against y1 going to SWF of y2. And I forgot to do part of the suspension, which I'll just add in. And indeed, these glue together in the expected way. So if you take the Bauer-Fruta invariants and you compose them, so even though you have different suspensions, it still makes sense to suspend the whole thing and then compose. So these two maps are actually composable. But yeah, if you take the composite of these two, it actually is going to be the Bauer-Fruta invariant of the slightly larger thing where you would close it up. So the Bauer-Fruta maps, they sort of form like a TQFT that assigns spaces to three manifolds, roughly speaking, and assigns maps of at least stable homotopy classes and maps between spaces to cobordisms. So in principle, you'd like to be able to use this to calculate the Bauer-Fruta invariant of a closed four manifold. Not that anyone has successfully done that yet. Bad sign. But before you can do that, so before you would try to calculate the Bauer-Fruta invariant for a closed four manifold, you would first have to reflect that you hadn't, at this point at least, we haven't calculated any SWFs. So if you can't even calculate those, then you can't calculate the relative maps. So let's talk about some SWFs. Right, so there's at least one good example one should check, which is the three sphere. An SWF of the three sphere is the zero sphere. Right, S3 also it has a unique spin-C structure, which is spin, so this is actually the zero sphere is a pin2 space. And at first this is very encouraging because you could say, we just take our space and then we desuspend 3 times. If only it were that simple. But okay, that's not how it works at all usually. But let's do some other good examples. SWF of a lens space is LPQ. Well, for each spin-C structure, you're going to get a different. For each spin-C structure, you're going to get a different sphere that has some dimension depending on an invariant associated to what spin-C structure you're in. So each of the spin-C structures gives you a different output. But that's still not very interesting because these are just shifts of S0. You just took S0 and you changed the grading, basically. You can think of suspending by C as sort of moving something that started in dimension 0 now gets split in dimension 2. Another good example is sigma T235, which is, there's a small chance I got the conventions correct, but this is just the it's a two-sphere that we already saw with the rotation action. But then, in keeping with the theme of some of yesterday's talks, let's talk about, other Seifert spaces, and especially a Seifert space which has appeared many times. So we could take SWF of sigma 237, which is, in many ways the first non-trivial three manifold. And all of the calculations that are written here are done by just explicitly understanding what all of the solutions of the Seiberg-Witten equations are. You can't do that for very long, and we're about to reach the limit of it. But you can calculate this one by using Mravka, Ajvat, and Yu gave a very specific understanding of the monopoles on the space, and it's going to be the infamous double banana phone picture. Usually this space is drawn where the pin to action goes like this, and J goes between the two different two spheres. So each of these sides is a two sphere, and J just is reflection about the axis. So this is a pin2 space because there's a unique spin-C structure which is spin, and this is a pretty reasonable space. It's just not that scary. But again, it's calculated explicitly. And you can use the same explicit calculations, basically due to MLY, to calculate SWF of sigma 2, 3n for all n, and it's just that you put in more phones. Well, I guess I should use a different color. More phones. They always have to come in pairs so that J can act continuously. But yeah, it's not such an interesting space. But you can also think about this like a homotopy theorist. So instead of drawing the picture, you can say, how could I express that as a diagram? And one way of expressing just the single copy as a diagram is that it's a wedge, or it's a push-out. So right, you have two copies of the complex sphere, one on each side, and you could just include the north pole and the base point from here. You could include that to the left sphere, and you could include it to the right sphere, and then you could glue those two spheres together along those points. And that's exactly what this push-out means. So this push-out is actually SWF of sigma 237. And if you want to include the other telephones, you can do that by doing an iterated push-out. You would add on another S0, and you'd go like this, and then you'd push out again, and so on. And so you just make a long chain of continued push-outs. But all right, fine. So you want to sound the pattern geometrically there. And for a while, those were the only computations of SWF of anything, because it's hard to get actual calculation tools to work on this. Although, it should be noted that Lidman and Manolescu proved that the homology of SWF agrees with the Heegard-Floer homology. And some people like Heegard-Floer. Not everyone has to like Heegard-Floer. But Heegard-Floer has been calculated in many interesting examples, but some of the techniques don't go over so well to working with spaces. And generally, you could imagine it's a lot harder to figure out what the space is than figure out what the homology of the space is. But also in yesterday's lectures, we heard about lattice homology. And it turns out that at least part of lattice homology works out just fine in the spectral setting. So maybe without saying anything about the proof, we could say that instead of trying to understand the moduli spaces explicitly, you could just basically you could look at the lattice chain complex of your four manifold, or of a plumbed four manifold. Unfortunately, we don't have to say what a plumbing is from last time. So yesterday, we talked about plumbings, or in Sergey's lectures. And there's a special class of plumbings called AR plumbings, which were really floating around in his lectures in the background also, where there aren't where the weight of the vertices in the plumbing tends to be lower than the valence of the vertices. And when this happens, it's known that the Heegard-Floer homology becomes much simpler. And then you can sort of port over techniques from Heegard-Floer homology to try and understand the Floer spectrum. So this is work of Irving Dai and Hirofumi Sasahira, which has a really negative outcome, I guess you could say. That this pattern actually continues. So SWF, if you plug in any AR plumbing, including all Seifert spaces, you won't necessarily get the exact same description as above, but you'll always have a description of the following format, where you have some sequence of numbers, n1 through nk, and some push out that looks like this. So where each of the top row is some sphere, and you just include that sphere into these higher dimensional spheres on the bottom row. And if you take the push out of that large diagram, so using some ideas from lattice homology, you can see that push out will actually be SWF of the space you put in. So this is true for any negative definite AR plumbing. that the SWF spectrum of the 3 manifold that's the boundary of that plumbing is just going to be the push out of a diagram of this form. And there's a reasonably explicit way to figure out what those NIs are. So that was all to say that even though at first you were calculating them in a geometric way by actually understanding the monopoles, you can also use kind of combinatorial techniques to see that the pattern that you actually thought was coming goes through. So yeah, it's not clear, this probably doesn't get you very far if you actually wanted to compute the Bauer-Fruit invariant of a closed 4 manifold, but at least they're not very difficult to calculate for ciphered spaces. But yeah, I think that's a good place to stop. So yeah, feel free to talk to me afterwards, and yeah, thanks for listening.
Questions?
Yeah.
Can you please say again, what was the precise relationship between these spectra and the ones coming from lattice, lattice chain complex?
Yeah, so it's, I don't want to say something that could be interpreted as too much. So, but there is a way to just, if you take the lattice chain complex, I mean, there's various ways that you could think of a spectrum that has the same chain groups as the lattice complex. And the point is that at least if you have an AR plumbing, there's like one very good candidate that has the same chains as the lattice complex, but as a spectrum. Basically this one, essentially. So if you have an AR plumbing, there's a certain very natural spectrum that you can construct that has the same chains as the lattice complex in that case. And then you build a map in from that spectrum in a way analogous to how it's done in the Hegardt-Floer setting. Some things become harder, but a lot of it just goes through. Ideally, though, I mean, you should be able to define a spectrum for any lattice, but it's actually a lot less clear that would work. So, yeah, but in the AR case, there's very few ambiguities. Does that sort of answer your question, actually? Okay, cool.
Other questions? Okay, so let's thank Matt again for the whole experience.